Making Soils Data Actionable webinar series. I'm Danny. I'm the Senior Soil Scientist at the Washington State Department of Agriculture, and I am so excited to welcome you all today to talk about soils data. If you have been working in this space, you've probably noticed that more soil tests and data are available to farmers than ever. And while this can be empowering, it can also be confusing. New information on soil chemistry, biology, and physics can sometimes be difficult to translate into action. And so the Washington Soil Health Initiative has put together this series to showcase how useful and necessary soils data can be to making in-field decisions. Every Wednesday at noon this month, we will be showcasing projects from across Washington that are using real data to make real-world on-farm decisions. Today, we have Troy Peters here to help us understand how to make soil moisture indicators actionable. Troy is a professor, scientist, and licensed agricultural engineer working at Washington State University. For the last 18 years, he has worked at the Irrigated Agriculture Research and Extension Center in Prosser. So for everyone in the audience, there will be a Q&A at the end, but feel free to post your questions into the chat as we go. You can find the chat feature at the bottom of your screen in a little thought bubble icon. Thanks for being here today, Troy, and feel free to take it away.
Okay, thank you. Hopefully everyone can see me and hear me. Yes?
Yeah,
Okay.
great.
Okay, so we wanted to talk about soils, and then in particular, I wanted to talk about how they can be used for irrigation water management. So with that, I wanted to talk kind of the basics about the soil-water relationships. And then, so the two questions that we wanted to know for irrigation water management is when can I turn the water off? Usually people say they want to know when they can turn it on and how long to leave it on. But in generally, especially in Eastern Washington, where they just irrigate almost all the time, it's kind of when can you turn it off and then for how long? And then a lot of people are just kind of looking at the soil, kicking the dirt, and making guesstimates, or wait until the plants get water. They are visibly water stressed, and then they turn the water on. But when they do it that way, they tend to either cause water stress to their crops, which means they cut their yield back. They're not getting as much growth and production out of their crops as they would like, or they're over irrigating and then causing resulting basically in a lot of deep percolation. So what kind of data can we use for irrigation water management? So there's soil-based, which is what we want to focus on today, which is based on soil moisture sensors. And then there's weather-based, which is using evapotranspiration and crop coefficients. And I'll briefly cover that just for information. And then there's plant-based methods, which use sap flow gauges and stem or leaf water potential, and or the canopy temperature can be used as a indicator of plant water stress. So I'll also talk about that briefly. So soil is basically little bits of rocks, and then because they can't compact those rock completely, there's little gaps and space in between the rocks where all the action happens. If all that space between the rocks is filled completely up with water, we get mud, basically, and that's called saturation. So that means that the soil is saturated. You can't get any more water in the soil than that. However, if the soil is left to its own devices, the excess water will kind of be pulled out by gravity, and it comes to a spot where the soil is able to hold on to that water against that pull of gravity. And it has to do with a couple things. So water is a polar molecule. It has the two hydrogen atoms are on the one side of that oxygen atom. And what that means is that it has a positive side and a negative side. So the positive side of one molecule sticks to the negative side of the molecule, which sticks to the positive side of one or other uh, other molecules. And so it kind of tends to clump together, which is why you can see, water droplets will they coalesce. Why, if you sprinkle water on the table, it'll group up and it'll pull into a bubble, into a droplet. This is why water sticks to your body when you take a shower or something. You need a towel to dry it off. And actually, and so and but so the molecules stick to each other, but they also stick to other polar surfaces. So think about when you're drying your hands off, or after a shower or something, you're drying yourself off with a towel. What it's doing is that water is sticking to those fibers, and then it's pulling the other molecules in behind it, and it pulls that water away from your hands. And that's how it dries you. So this is the exact same mechanism that soil uses to hold water. It holds onto those soil particles and it pulls the other molecules in behind it, and it allows that soil to hold on to water. So the maximum amount of water that soil can hold long term against the pull of gravity is called field capacity. So field capacity isn't, I mean, you can put more water in the soil than field capacity because it can go up to saturation, but field capacity is the maximum amount of water that soil can hold against gravity. So once but the roots can pull the water away from the soil and absorb it up and use the water, or that water can be evaporated from the soil surface, and that reduces the water. And it'll come to a point where there's still a little bit of water left in the soil, but the plants, just no matter how hard they pull, they can't get that water away from the soil, or the water is held in such little tiny cracks, and it's really far away from, far meaning in relative terms to the tiny root hairs and soil particle sizes, but far away, so that it just can't get that water away from the soil. And then the plant can't get any more water and it wilts and it dies. So this is permanent wilting point. So even though there's water left in the soil, we don't want to get to the permanent wilting point. So this means that um, between field capacity and this permanent wilting point, this is the point, this is the water content that we want to manage for plant growth. If you continue to dry that soil down, if you put it in an oven and you cook it off and make sure that there's no water left at all, it gets to oven dry. However, that water here is unavailable. So this is available water. Again, this is what we are interested in. So the available water, this is kind of, in this case, we kind of, in two dimensions here, we say, okay, that's the width of this bucket. And then we also have the root zone depth. So the deeper, if I have a tiny newly planted grass seed, then my root zone depth is really shallow. But as the roots grow and grow, it has access to more and more soil. And so basically the size of that bucket gets bigger and bigger and bigger. And the amount of water that the soil has, the plant has access to in the soil gets larger. So the water holding capacity of the soil is the water holding capacity of the soil times the root zone depth is the size of this reservoir. So this is kind of in this two-dimensional bucket here, we can see this is the size of this bucket. If you put more water in the soil, it looks like, I mean, it makes you feel good. I mean, the water goes in the soil, but if the soil can only hold so much water, and if that water will keep going, if it's at field capacity or exceeds field capacity, that water will keep moving down, and it can move down past the bottom of the root zone, and that water is lost. So you wasted your time and energy and money, and also you probably rinsed out a lot of nutrients out of your soil when you did that. So that's not a good thing to over irrigate. So in this case, in our little example here, we're overflowing the bucket. You can definitely overflow the bucket. The bucket's only so big. ET, which is water out, that's how the water actually comes out of the top of the soil, but this is the evaporation and transpiration, which removes water from the soil water holding from that reservoir. And so in order to do water management for crop growth, we need to know what this soil water content is. And so there's two ways to estimate this. One is we can get an estimate of how big this bucket is and then try to keep track of ET and say, okay, every day we got this much water out, and so our water level, we're basically modeling where how that water level drops in the soil, and then we keep track of how much water we put in and when we put it in, and then we can use that as kind of the checkbook, which, okay, money out and then money in, as same as water out and water in, to do water management with that. So of course, different soils hold different amounts of water, and this has to do with the locations or how water is held by soil. It's primarily held in the spots where the two soil particles come together. So if you stick your finger on water or on the table, you can see that it sticks to your finger and also sticks to the table. And then there's the meniscus, or the point where the two come together, is where a lot of that water is held. So in other words, the more spots in the soil where the soil particles are coming together, generally the more water a soil can hold. So if you extrapolate all the way up to like a bucket of gravel, and then you pour water in that, of course the water goes in very quickly because the pore sizes between those gravel particles is very large, goes in very quickly, but it goes right out the bottom. And if the bucket has a hole in the bottom, obviously, then it goes right out the bottom. And then it still holds a little bit of water because the gravel is wetted. And then the spots where those rocks come together, it can hold it there, but just not very much. And so this is the same with a coarse sand and fine sand. The smaller the particles, the more of those sites where those two soil particles are coming together, and that's more, it means it can hold more water. And when we do irrigation water management, we like to do things in terms of one dimension. So just like when we measure rainfall and snowfall, you just do it in one dimension. Okay, we had a half an inch of rain. We do the same with irrigation. We have a half an inch of water was used. Okay, let's apply a half an inch of water to put it back, and that gets rid of the size of the field and allows us to kind of make it a little bit more universal in terms, instead of thinking of things in terms of volume, think in terms of 1 inch or one dimension. So one way to the water holding capacity, an easier way to think of that too, is the inches of water that the soil can hold per foot of soil depth. So inches of water that it can hold between field capacity and wilting point per foot of soil depth. So like a silt loam soil or something, about 2 inches of water per foot of soil depth is kind of a rule of thumb. Sandy soils are going to be about 1 inch, so about 1 inch of water per foot of soil depth. And it just means that these going to have smaller buckets, right? And the other thing to notice here is look at the range, 1.8 to 2.8. That's huge, and that's because it's not just the soil texture or the size of the soil particles that matter. Soil structure also matters, and how much organic matter is also in the soil can affect how or tillage and things you do with the soil can affect the water holding capacity of that soil quite a bit. And so that's just something to think about. You're kind of stuck with the soil you have, at least in agriculture you are, but you can change that by managing it to increase the organic matter content, to do things so that you don't constantly destroy that soil structure, and you can increase that water holding capacity. So one thing so if I have a deep soil or a deep rooted crop and I have a silt loam soil, then I have a large water holding capacity. I have a large bucket. I have a deep soil, same, but it's a sand. I have a smaller bucket, or a shallow rooted crop or a shallow soil. Maybe it's just rocky down here and there's just not much soil there. Then I have a smaller bucket, and then a shallow sandy soil here also is the smallest bucket of all. The thing to pay attention to is the amount of water that that crop needs to grow to be healthy and happy does not depend on the soil. ET is going to be the same regardless of the soil. So a common misconception is, oh man, I have this shallow sandy soil out there. I see water stress in there all the time. So what I'm going to do is I'm going to put in some extra big sprinkler nozzles in that area, or I'm going to double the amount of drip tubing. So when I apply the water, I apply twice as much water. So I just put more, I really got to pour the water to that shallow sandy soil, so that, because I always see water stress, it must need more water. Wrong. The problem is you run out of water very, very quickly. It's not using more water, it's just running out of water more quickly. And so you need to water less, but way more frequently, twice as often, half as much, or in order to uh, make sure that it doesn't run out of water before uh, before it becomes water stressed, and then you're filling it up. And when you fill it up, you're not overflowing the bucket. If I apply twice as much water here, all of the extra water that I apply is going to also be lost to deep percolation. It's going to be throwing good money after bad to me to try to fix that problem. The other thing to pay attention to, so here's field capacity. So this is the full soil maximum amount of water that soil can hold long-term against the pull of gravity. Here's dead plants, don't want to go here. As you dry it down, it's easy for the plants to get water away from the soil, and it doesn't hurt their production at all. But after a while, the plant starts to struggle. It can't get the water away from the soil at the same rate that it needs it, or it's just, and so the plant starts to shut down. It curls its leaves, it closes the stomates. It's trying to limit its exposure to sunlight and energy so that it reduces the rate that water is lost as a way to protect itself. And so we lose this maximum production, but it also reduces the water use rate, but it also reduces the yield of the crop. So what we do is we pick this MAD, maximum allowable depletion. We say, okay, at this point, we're going to begin to see water stress. And so we don't want to go below this point. Or in some cases you do, and you're like growing wine grapes where you're deliberately imposing water stress, and then you're over here on purpose. But generally people want to keep it between field capacity and this MAD line. And 50% is kind of a rule of thumb for many crops, not all, but many crops, as the water, how much water you can deplete of this total available water holding capacity before you're going to begin to see water stress for that crop. Some crops like alfalfa are very water stress tolerant, and you can deplete 60 or 70% of the water. Some crops like potatoes or onions are not very water stress tolerant, and you deplete like 30% of the water and it's begin to show water stress. So soil moisture sensors. So this is the best way that we know of to know how much water is in the soil that we can use for irrigation water management. And so is because we just measure it. First of all, where do we put them? So what things we don't want to do is put them right at the edge of the field, because crops at the edge of the field are doing funny things. Sometimes if they're right at the edge, then they're getting water from underneath the road or whatever they're next to that doesn't have crops pulling the water out from there, and so they grow more vigorously. Or sometimes because the hot air is coming across this arid area, and then it's hitting the edge, the crops right at the edge of the field, And so it uses more or less water. In other words, it's not representative of the field. So you don't want to put it right at the edge of the field. You want to put it in a ways to where it's representative of more of the field. And then it depends on what you want to do. You can either choose the average soil condition. And so if you have all these different soils in your field, maybe you would want to pick, okay, this is kind of the average condition, so we'll put it here. Or if you just say, hey, I want to make sure that I get the best yield everywhere. And so I'm going to put it in this soil and I'm going to irrigate such that I irrigate before this soil experiences water stress, and I irrigate in such a way that I don't overflow this soil. And then the rest of these soils are going to be fat and happy. They're going to be fine. They're also not going to see water stress. They're also not going to see water loss to deep percolation in those soils. So it kind of depends on what you're trying to do. If you want to maximize yield everywhere, this is where I would put it, the lowest water holding capacity soil. If you're kind of doing things with deficit irrigation and you just kind of want to see the average soil condition, then you might want to put it there. Then at the depths, let's say if I have one sensor, or I've had two sensors or three sensors. If I have one sensor, I kind of, at the depths, if I only have one depth, then I would want to put it in the active root zone. So obviously most of crop roots are at the top near the, near the soil surface. And then as it goes down, you can find trace roots way down deep, but most of it's up here. And so the rule of thumb is if you divide the crop root zone depth into quarters, then 40% of the roots are in the top quarter, 30% in the next quarter, 20, 10. 40, 30, 20, 10. If you add those up, it's 100% in that. But again, most of them are at the top. So if I have two, so if you have one sensor, you'd want to put it there in the middle of that. If I had two sensors, you want one in the middle that'll show kind of a lot of the soil water dynamics and how that changes drastically over time. But this sensor down deep is going to give you a lot of information. What it's going to show you is if I irrigate, and every time I irrigate, this sensor doesn't move. What does that mean? It means that the water I applied never got down there. That's interesting and that's relevant. If I irrigate, and every time I irrigate or every time I have a rainfall event, this sensor, it lights up, goes up, and you see that water go past, that means I'm putting too much water on. So that sensor down deep is also interesting and relevant. And so if I was going to pick one, putting one down at toward the bottom, or even right at the bottom of the root zone, is going to give you a lot of information that's going to be useful for you. And then if you have three sensors or more, you just kind of divide that up however you want to kind of represent that whole profile. Let's talk about the different types of soil water sensors. So these measure tension. So there's two things we can measure with soil moisture sensors. One is soil water tension, which is how hard the suction that the water that the soil is pulling on the water. So if I have water and I put it in my hand and I take a dry rag, I can suck that water up off of my hand. It pulls it out. And so that cohesive and adhesive forces between the water molecule holding onto the soil particle and then pulling its buddies in behind it, it's a suction, and we can measure that suction directly with a tensiometer. And here is a tensiometer. And this one has a broken tip, which I like. Actually, here's one without a broken tip here. I like it because it shows you what is inside. And so basically this is just a porous ceramic material, and we fill this up with water. Oh man, I need to maybe turn off the, anyway, I'll try it. Just put it in front of me. Fill it up with water, and then when this gets full of water and I bury this tip, it gets in contact with this soil surface, and the soil, that soil water tension, pulls water out of this, out through those pores in that tip. And when this is full of water, the it can move water through it, albeit slowly. It can move water through it, but the pores are so small that you can't get air bubbles in there. And so it'll pull water out of this and create a vacuum in here inside of this tube. And then we just measure the vacuum right here. This is a vacuum gauge that we use to measure the vacuum. And a bar is a unit of pressure or vacuum. About 1 bar is equal to about 14 psi or 1 atmosphere. And 1/100th of a bar is a centibar, and that's the units that are most of these are measured in is centibars, 1/100th of a bar, which is a measurement of vacuum. So a good thing about tensiometers is that it gives you that soil water tension. The soil water tension is the same force that the prop has to overcome in order to pull that water away from the soil. So that's relevant to the crop. These are less expensive, although not inexpensive, just less expensive. I haven't priced them for a while. I guess I would estimate they're probably 70 to $100 each. I have no idea. Widely used, studied, and accepted, and they're not affected by salinity. So a lot of these things that are measuring the electrical properties of soil and are affected by the salts in the soil, but this is not. It samples a fairly small area because it's just kind of what's around the tip. And then it indicates when to irrigate. So that's the soil water, the plant water stress. And it can't really tell you how much water to apply. So if you're using tension, tension gives you when. Volume, if you're measuring the soil water volume, which I'm going to talk about in a minute, that shows how much. You can use that to indicate how much water to apply. So another sensor is a resistance sensor. That's this one here. This is they look like this. Basically, it's got two conductors in a piece of gypsum. Gypsum is the same stuff that's in wallboard that most of the insides of your homes and offices and stuff are made out of. And it measures the resistance between those two conductors that are stuck in that piece of gypsum. Water conducts electricity, and so the more water that's in that piece of gypsum, then the less resistance that there is between those two conductors. And in this case, this one has that same piece of gypsum in there, but it's kind of encased in sand, and they do a lot of things to try to make it so that to increase the area, the soil that it's exposed to, and to make it a little bit more uniform, uniformly packed around that sensor that's in the middle in order to decrease the variability between these sensors. There's still kind of a lot of variability between them. Like in other words, they put one here and put one here, they might be different numbers, but I'll talk about how to deal with that in a minute. Resistance sensors. So these are inexpensive. They give also usable trends. They give the soil water potential. Again, that's that tension. And it's easy to log data because you can wire them up to data loggers, and it can be wired up to telemetry, and it can be, you can look at it on your phone if you have all that set up. It is affected by salinity because, of course, salts help water to conduct electricity, and then which will affect the resistance between those two conductors. And so it does give imperfect accuracy. In other words, just the repeatability is kind of difficult, and then samples a small area. And here's an example of a water meter that you would use these two alligator clips to clip onto the two leads that come out of that. It measures that resistance, and it applies a polynomial to convert it into soil water tension in centibars. So in this case, it's reading 25 centibars. So what do we do with these types of sensors? So as a starting point, 30 to 50 centibars of tension is usually a good point for to irrigate. So low tension, which means if it's zero, this means the soil is full of water. And as the tension increases, it means that it's drier and drier. So a high number is bad in this instance, at least if you're trying to impose water stress or trying to avoid water stress. And a low number is full. So 30, anything above 30 to 50 centibars is the irrigation for no stress, and then increase that to 80 to 100 centibars for higher or imposed water stress. And then what we do is, because maybe there's the repeatability issues, etc., then you just correlate those numbers to the crop condition. So I go out there and I'm looking at my sensor and it says 50 centibars, but I'm looking at my crop and it looks like it's water stressed. Then I say, okay, 50 centibars is not my number. I want to irrigate at 30. I want to irrigate before it reaches that number in the future. And then, 3 days from now, it's 20 centibars, and I say, oh, okay, and it's dropping, so it's getting close. You can get an idea of when to irrigate based on that. And then watch that deep sensor after an irrigation to indicate that degree of the depth of the penetration, how deep the water went. So here's what the soil profile might look like in this case. So the soil water content, the soil water tension increases. They built the graph upside down, which is you can do it either way, however you want, but they did it as a tension. So a tension is a negative suction. So they are negative pressure. And so they just did it negative, which is fine. So you can see that the red one is probably the shallowest because it gets driest the first, and the pink one is probably the deepest soil moisture sensor. They irrigate, and you can see all of those sensors moved, which means they may have over irrigated in this case. They went all to zero, go back down, up to zero, back down, like this. So anyway, you can use those numbers to kind of give you an idea of what's going on. Capacitance probes. Here is this one. Is a capacitance probe. It looks like this. And then a lot of them work along similar principles. In this case, this sensor is placed into the soil. And what it does is it measures between these two conductors. It's measuring the capacitance. So the capacitance is an electrical property of all materials that indicates how much electric charge that it can hold. It's the K factor, if anybody knows anything about electronics. But it's an electrical property of soils. You can measure it using variations in frequency across those two conductors. And that's a function of the volume of water that's in the soil. So these are measuring soil water volume. So you can do them different ways. This one is like this here, oops. And then as you, oops, you can pull it out. And then these are these sensors that are in there. And again, it's just measuring the capacitance between these two conductors as it's contacted with the soil. Inside of here, it's measuring through this plastic and into the soil. And then this is installed into the soil. One thing that's of interest is the end of this. This is a sharp cutting edge because any gap between this sensor and the outside soil can cause quite a bit of variability in the readings. And this is kind of a major weakness of capacitance probes. I'll talk about that in a second. Here's one. In this case, this one slides down a tube, which is the way that this is meant to, you slide it down a tube and then you take different measurements at different depths. And then you move it to the next tube and you slide it down, etc. So what happens is it's measuring the capacitance between these two conductors in the soil. And of course, it's going to measure, but if what happens is that although if the soil was completely dry and I brought a wetting front near it, I would begin to see that these numbers start changing maybe about this far away from that sensor. But in reality, what it's super sensitive to is what's happening right here, like within a couple millimeters of these two conductors in the soil. So if I install that wrong, there's a gap between that sensor and the soil around it, or or I wiggle it, or a worm goes by or something like that, it's really going to affect that reading quite a bit. So good thing about capacitance sensors, it gives that soil water content or volume of water that's in the soil, and it's easy to log that data. Again, we can hook it up to electronics and make it work that way. It samples a fairly small area, especially it's very sensitive to what's immediately next to that sensor. So installing it properly is really important, and it's not always easy to do. It can be expensive, and this proper installation is critical, and it is affected by salinity and temperature, because both of those things can affect the electrical properties of the soil. Time domain reflectometry is another way to measure soil moisture sensors. Soil water, here is one actually that is uses these same principles, but what it's doing is it's measuring how fast a pulse comes down, and it gets reflected off the end of that wire, and it gets measured in this other wire. And so how that works is fairly complicated, and it uses fairly sophisticated electronics. So what they're doing is they're measuring the scale of this electrical pulse as it goes down off the end of that thing. And look at the 10 to the negative 12 seconds. So if you know negative 12, which means it's smaller than micro, smaller than pico, is measuring the electrical product on a very, very tiny time scale, and getting the exact look of this profile. However, they've worked out a lot of those, and then the cost of time domain reflectometry sensors is going down. So actually more and more sensors are using that same principle. Here's one. They also call it time domain transmissivity, which is kind of similar. If you're really interested, you can dig into the differences with that. Well, so these sensors give the volume of water in the soil, and the problem is, so you get a number, let's say it says 35%. What do I do with that? What if it says 38%? I don't know what to do with that. So in order to, and because that number is going to be different for different soils. We just talked about how sandy soil doesn't hold as much water as loam soils, and how soil structure and organic matter content can affect the water holding capacity of soils. So these numbers are relative. And so because they're relative, if it's wrong, in other words, let's say I don't install it properly, exactly right, it's still relative, as long as that number changes and it doesn't exhibit hysteresis, which means the wetting cycle, when it comes back to the same spot on the drying cycle, it gives you a different number. Then it's still usable. And so what we want to do is we want to know two things. We need to know what field capacity is according to that sensor, according to that soil, where it is installed. So we need to know that field capacity, or that full point. And the easiest way to do that is just irrigate, put a lot of water on, and as soon as the soil thaws, or after 24 hours after heavy irrigation, let that water go through, and then the soil should be at field capacity by definition. It's holding that water long-term against the pull of gravity. Just a note, it's easier to do this in the spring when ET is almost zero, or it is zero, than it is during the season, because the constant movement of water in and out because of ET moves that number so much that it's kind of hard for it to hold still long enough for you to say, okay, that's field capacity. So we need to know what field capacity is. And if we know what field capacity is, then the difference between a current reading and what field capacity is, that is what our soil water deficit is. And then the other thing we need to know is, what is the MAD point? When is it going to experience water stress? And a rough rule of thumb is that if we go all the way back to the permanent wilting point of a soil is about this permanent wilting point is often, it's about half of field capacity in general. This graph, I need to fix this because it's usually up here. It's about half of field capacity. And what that means, and if I choose my MAD point to be half of that, then half of half, and so about 75 to 80% of the soil water depletion will give you a rough, or of the field capacity, not depletion. So let's say field capacity is 40%. That means at 30%, which is 75% of 40%, that is where the you might be a good idea to do that. And then you do less of that for vegetables. And then again, what we want to do, because those rules of thumb don't apply for everything, especially for sandy soils, that doesn't work. But you can use table-based values for that water holding capacity of a soil to say, okay, sandy soils use, what, here's my field capacity, and I looked at it from the sensor, and the value that comes from the sensor is actually the most useful number, because we don't know exactly what it is, because most people don't test what field capacity is for their soil. They just look at the sensor. And if that sensor is installed a little wrong, it's still okay and it's still usable, because what we want to do is the difference between that field capacity and its current number is the number we're going to use. And then we say, okay, the water holding capacity, and then 30 to 40% of that for vegetables, and then 50% of that for other things. And then we refine it with our experience. We see, oh, I thought it was going to begin to experience water stress at 25%. It's at 20%, and it's still fine. It's fat and happy. Okay, we revise that based on our visual observations from the field and other things. The other thing we can do, so here's the soil water content over time. This is for a soil volumetric water content sensor. So this is just one sensor. A couple things you can see. This wavy line happens for a couple reasons. One is this is when the sawtooth period here is about 1 day. So during the middle of the day, that's when ET pulls water out of the soil, and that's when it's going to drop. And that either comes up at night because the soil is redistributing water to those drier areas. In other words, it's moving it back into those areas that it was pulled out from by the plant from areas that have more water. Or this sensor is temperature sensitive, and the temperature swings from day to night are causing that that to move up. We're not quite sure. The other thing that happens, so here was a rainfall event, here's an irrigation event, brought the soil water content up, brought it up. Here, this is interesting here to me, because it went up, came down quickly, and then it came down. So to me, this means that this happened because we exceeded field capacity. It was at saturation, and then this decrease in the water content, it was because that excess water was just draining through the profile at that time. So we can exceed field capacity with our irrigation events, but we don't want to irrigate to that point. So in this case, they drew the blue line here as field capacity, but I would probably move it down to here about 12.5. And then my current, if I want to, so if this is today, I want to irrigate, I look at difference between here, 12.5, and my irrigation, 11.5. Oh, okay, put on 1 inch of water. Here's some other examples. I'm kind of running short on time, so I should speed up. And then the look and feel method, which is the good old, you dig soil up and then you look at it, you try to form a ball, you try to push it into a ribbon, you see kind of how the soil adheres to each other because water helps the particles, because that adhesion and cohesion between the water also causes the soil to kind of stick together as well, which is why wet soil you can form into a ball. You can sometimes push it into a ribbon. If you bounce it on your hand, it'll either fall apart or it'll stick together. You can use that type of experience, the look and feel method, to it's definitely a subjective way to do it, but you can get better at it with time for your particular soil. And then what I would do with this is do it the same way. Take the time and experience to train yourself to do it correctly. The two things you need to know is what is field capacity, when does it look, what does it look like, and what does it feel like when it's at field capacity? And you need to know what it looks like and what it feels like when you begin to experience water stress. So dig up some soil when it's at field capacity, look at it, feel it, bounce it around. Dig up some soil when at the first time you ever see water stress, look at it and feel it, and say, okay, I want to manage it between those 2 points. And so you can do it with this look and feel method if you're kind of systematic about it and you train yourself. The other thing is, I mean, going, 6 to 8 inches is not a big deal, but a lot of times getting soil from, 3 feet deep, people don't want to dig holes that deep. So you need to get a soil probe that allows you to pull soil from those deeper depths, or figure out a way to not just look at what's happening at the top part of the soil, but the entire root zone. So one thing I wanted to, so neutron probes I didn't talk about, but because they're kind of mostly a research tool, or consultants use them sometimes. They do give you, it's a different mechanism and it gives you the most correct answer, but most people don't want to manage the paperwork and dealing with a radioactive device. And so they don't use those. So, but most sensors will give you a trend that's usable for irrigation scheduling. And then proper installation of those sensors is critical and must be done right to give you good data. And then actually using the sensor is important. People install them and then they kind of ignore them, which is unfortunate. And then the other thing is to keep records and calibrate yourself using numbers, that crop response, and your experience. So like I said, you can get better at it over time. And then if you there's consultants that will do this for you. You hire them, you ask them a lot of questions, and then you eventually you might not need to pay them in order to get the answers that you want. So with that, I am going to stop sharing and answer questions.
Okay, thanks so much, Troy. We have 11 minutes and 13 questions. So I've
Okay.
tried to kind of rank them based on their applicability to the most people. So from Savannah at South Yakima Conservation District, we want to know, how many sensors do you need for a field? And does that depend on soil type and acreage? What is your advice?
Because of the price, I can just tell you what most people do is because of the price of them. Most people use just one. And then, so in science too, we say if you only have one sensor, it's right. If you have lots of sensors and they're different, nobody knows what to do with those. And so that's what I would do, is this one. And in fact, I would do it at two depths and in one location per field. If I was managing it for it was my money and it was my field, and that's what I want. That's what I would do. And again,
Okay,
one at the deep point and then one in the middle.
that's a great transition to some questions we have about return on investment. So, from your perspective, is there a good return on investment for installing these? And do you know if there are studies or data available about the ROI?
Yes. So, and the answer is it depends on what you're growing, honestly. So, some crops are very sensitive to water stress, and so and yield and quality drive the ROI numbers like nothing else. So if I have a field pivot full of potatoes and I get it wrong, it hurts a lot. But if I have a pivot full of alfalfa and I get it wrong, maybe it's not that big of a deal. So primarily the ROI is strong for vegetable crops and not so strong for low value like forage and grain crops, honestly.
Okay, and someone had a question about the sensors in fruit trees. So maybe you can talk about that and more broadly about just sort of annual versus perennial.
Sure. So annual crops are great with soil moisture sensors because they you don't have to dig them up every year. With I mean, did I say with perennial crops you don't have to dig them up. With annual crops you do. You have tillage that and the sensors are in the way, and especially if they're in forage crops and you're trying to drive around them with harvesters and things. But in perennial crops like tree fruit and grapes and hops and things, then it's great because you just tie them to a trellis wire or a pole or something, and it's there and it's out of the way and you can keep using it. Also, annual crops have a growing root zone, so the bucket depth gets big, and then it goes to zero, gets big, and then a perennial crop has a fairly static root zone depth, which is also useful. So that strengthens the ROI for uh, perennial crops. Also, perennial crops like apples and pears and cherries and grapes and stuff. The the economics are tend to be stronger for those. Your your penalty for messing it up tends to be higher. Also, water management affects a lot of diseases like corking and uh, uh, what's the corking in pears, the bitter pit, things like this. So there's strong economic incentives to do it right for those.
Thanks. So once the sensors are installed, and you touched on this a little bit throughout your presentation, but how easy is it to interpret an action on the data they collect? And maybe you can talk even about some of the web-based or app-based data portals and how tech savvy you need to be to use them.
Yeah. So it so a lot of the sensors a lot of people purchase them from dealers like Wilbur Ellis or Simplot, or there's a lot of companies like IRZ that will install these for you. And usually what they do is they set it up with a telemetry system where there's a cell phone modem on the system that's out in the field, and it's reporting the data up to the cloud, and you're getting it on your phone and you're looking at it. And then all those apps and stuff look different, and you just kind of have to train yourself to use those. Um, but so that telemetry system obviously is going to cost you more than if you kind of put them in yourself and you just go read it with alligator clips or something like that. But it's you don't have to go out there and do it. So maybe it's better. It's worth it for some people. It's not for others.
Okay, so 6 minutes left, lots of questions still. Very popular topic. Maybe, well, okay, so you showed us a lot of options and you discussed the pros and cons of various options. if you were about to invest in this technology for your farm, what kind of sensor would you choose?
Um, for, if it was my money, I would do, um, the other thing is I want it to stay in one location for a long period of time because it wouldn't if I because a lot of it's kind of a relative number that I calibrate myself to over time. And if I dig it up and move it all the time, then I have to redo that. So I would want it to stay in one location for a long period of time. And so I'd want something that was robust and could stay there. I would use volumetric water content, some like a capacitance type probe. Um, and I think I wouldn't worry too much about what type of sensor it is, but just more. Um, and I would use two sensors, again, at in the middle or the top third of the root zone and one down at the bottom. And then, yeah, I think I would probably pay for the telemetry system just because it would be nice. I can check it every morning.
Okay, and we have some really interesting questions about AI or artificial intelligence. So maybe you can talk about what advancements you anticipate in this field in the near future, and if AI has a role in this space.
Yeah, that's a great question, one that we are actively working on, which is using AI to help interpret these soil moisture sensor signals and data so that it really is plug and play. I talked a lot about, okay, the kind of the mental thing you have to work out to interpret that. Um, the sensor signal in comparison, try to figure out where field capacity is and where your water stress point is. We think that we can use AI to develop these automatically, and so that it really is plug and play. And it just gives you, okay, today's soil water deficit is 1.5 inches. So if you're going to irrigate today, that's how much water you apply without them having to, okay, it's 37%, field capacity is 42%, all this stuff. So we think we can do that.
Awesome. Okay, so I guess unfortunately this is the last question. So really apologize to everybody whose questions we didn't get to. Um, But if you were trying to increase soil or when trying to increase water holding capacity by increasing organic matter, is there a point at which your soils sort of have a limit, or can you exponentially and linearly continue to increase water holding capacity?
Mm.
I
That's
know this is
probably a
very
question.
popular in the soil health space, and
Yeah, that's why it's probably a question for Danny, actually. I don't, there's definitely a limit, but yeah, what do you say?
I think there's definitely a limit. Organic matter accrual is important, and that can be done to an extent with management, and that can, to an extent, increase soil water holding capacity. But there are definitely like textural and climate limitations. Um, but you are the pro here, so we actually do have 2 more minutes, and we're going to
Okay,
ask another question. Um, so maybe as the last question, I know a lot of folks have kind of low quality irrigation water or salt affected soils. Can you talk a bit about the effect of salt on water holding capacity?
sure. So salt, plants have membranes on the roots, and when they pull the water out of the soil, they leave the salts behind. And then salts, if you have high salt on one side of a membrane and low salt, it creates an osmotic potential, which means that the clean water wants to move over to the salty area, which means that it's harder for the plants to get the water away from a salty soil than it is a clean water in the soil. So um, and so any water, if you have irrigation water that's salty, that those salts build up over time. And just the simplest way to do it is you deliberately over irrigate and you rinse those salts down out of the root zone. It pushes them deep. It delays the problem for some later date, but it's it's delayed, and there's really no way you can take the salts out of the soil that I know. So
Okay, that brings us exactly to 1 o'clock. Troy, thank you so much for all your expertise and for this presentation. For folks who are interested, we do have our final webinar in the series next Wednesday at noon. That is going to be specifically for users of the R programming language. So if that is not you, the talk may be a bit technical, but otherwise, please join us to learn about auto-generating soil health reports. And thank you again, Troy. This was awesome.
Thanks.